Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And also, we have a free MSE company database categorized by industry sector, location, as well as internship and full-time titles. So if you're interested in that, you can find the link in the description below.
Hey everyone, welcome back to the It's a Material World podcast. I'm your co-host Puneeth. I got my host David over here. How's it going, David? What's new?
Great. As people on YouTube can see, I have a different background again today. I'm at home to get a little bit of vacation before the start of the new school year. But yeah, just enjoying it. How about you, Puneeth? You look like you also have a more professional setup today.
Well, I think it's the same from our last episode, but it is much cleaner than it usually is. I'm still in the new house, still getting unpacked. But yeah, overall, things are good. Settling into the new city, St. Paul. It's just like 15 minutes from Minneapolis where I was. So it's not too big of a deal, but definitely something to get used to. Definitely driving around a lot more because uptown is very like walkable, whereas here in St. Paul, new neighborhood, more like suburban feel, but still very much like a city. It's kind of a blend. But yeah, just driving around a lot more, getting used to city driving. And that kind of takes us into one application of our episode today, which is focused on supercapacitors. And so we brought on the Vice President of Automotive and Business Development at Skeleton Technologies, Sebastian Pohlmann. And so we basically really just talked about supercapacitors, what they are, and how they contrast from batteries. And that was kind of key learning for me, is like there's really no stepping on other toes when it comes to supercapacitors versus batteries. It's just different applications. It's carving a niche within a niche. But yeah, I know you're very interested in the battery side of things. So what was kind of the most fascinating aspect of the episode for you?
Yeah, no, I agree with carving a niche in a niche, especially as the VP of business development. Most people might try to just like sell it as the best thing that will ever happen to the space. But I really enjoyed how he was very realistic and told us exactly where it would work and exactly where it wouldn't work. And I think that way is very clear about the limitations and also the great benefits. But beyond that, I think that their new technology, super batteries, were very interesting and provided kind of a bridge between what supercapacitors do well and what batteries do well. And again, that's a niche inside a niche inside a niche. And so hearing about where he sees the field playing out within the next 10 to 20 years was very interesting, and how energy storage as a whole will develop. Gave great insight into, I think, how the questions that we need to answer as scientists to electrify the world. So that was my favorite part. Is there anything else that stood out for you?
No, I think that translates specifically to the advice he gave at the end of the episode for younger material scientists, especially who are conducting research right now. It was very important and insightful. I think you guys should stick to listen into the rest of the episode, because he talks about kind of the consideration of costs and how that's not really talked about in a university lab setting, but it should be. And he goes into exactly why. So a lot of really insightful stuff in this episode. If you enjoy it, please leave a rating and a review on Spotify or Apple Podcasts. And if you're watching on YouTube, help us out by subscribing. We're very close to that 1,000 subscriber mark. So it would really mean a lot to us if you were to subscribe to the It's Material World podcast. So yeah, without further ado, let's get into the rest of the episode.
All right. Hello, everyone. We are very excited to welcome today's guest, Dr. Sebastian Pohlmann, VP of Automotive and Business Development at Skeleton Technologies. Sebastian obtained his PhD in physical chemistry from the University of Münster in Germany and is one of the top experts globally in supercapacitor energy storage. During his time at Skeleton Technologies, Dr. Pohlmann and his team have developed the highest energy density ultracapacitors to date. Thank you so much for joining us today, Sebastian.
Thank you for inviting me.
Cool. Yeah. So let's start off with the basics. So we just wanted to start out by learning what exactly is an ultracapacitor, and how does that compare to other concepts in the energy storage space, like batteries, for example?
Sure. So an ultracapacitor or supercapacitor, these terms are often just used as you like them. And these are basically high power energy storage devices. And what I mean with that is, if you compare it with a battery that you have in your phone or in your laptop, then you normally use that battery for maybe a couple of hours. You wish that you can use it for maybe 10 hours or longer or a whole day. So you have a fairly stable low power output over a long period of time. Supercapacitors are nothing like that. They have lower energy density, but very high power density. So those devices normally use for a couple of seconds or maybe for a couple of minutes, but then you need to recharge them. But on the other hand, you can get a lot of power out of them. And if you had a supercapacitor in your phone, then you could charge it in a second, but you could only use it for maybe 10, 15 minutes. So that's the reason why you don't have them in your phone. But it's also the reason why they are in a lot of other applications.
Interesting. And so when we talk about batteries versus ultracapacitors, batteries, their voltage, and which determines their energy and power density, is determined by chemical reactions. For ultracapacitors, how are those like power density determined for the applications?
Yeah, for supercapacitors or ultracapacitors, the energy that you can get into the device is determined just by the surface area that you can get in the electrodes. So batteries, as you just said, they store energy in chemical reactions. So you have a chemical reaction going on, the electrons being used up for it, or not used up, or used in it, and you can get those back later. In supercapacitors, it's charge separation. So you have a large surface area, you accumulate electrons on it, and you counter those electrons with a bunch of ions on the other side, the opposite charge. And then when you discharge, you basically take the electrons away again. And that, of course, is a process that is fairly quickly, because you don't have to wait for a chemical reaction to happen. But you can get the electrodes in there and out of there at will. That's why supercapacitors are so power dense. So that's why you can get the energy out very quickly. At the same time, it also explains why the energy density is quite low, because you just are limited by surface area and you can get only so much surface into the electrode.
And so another application of batteries is to overcome some of those issues. You can put them in parallel or in series. Is that also a application for ultracapacitors, supercapacitors to be linked together to overcome some of those flaws?
Yeah, absolutely. So it's of course not overcoming the energy density in itself, because that stays the same whether you go in series or in parallel. But of course, supercapacitors are never used as a single cell, or let's say rarely used as a single cell, but they are almost always used in series, and then of course also in parallel. So let's say you have an application where you want to have a 48 volt hybrid, for example. Yeah, so those specific type of car where you have a 48 volt energy port net, then you would put a certain number of supercapacitors in series in order to get to those 48 volt.
I was just about to ask, like, what applications can supercapacitors be used in? You just mentioned automotive. Can you dive into exactly what purpose these supercapacitors serve within the automotive application, and maybe even some other applications as well?
Yeah, sure. So automotive, there are actually a lot of vehicles on the road with supercapacitors today. Sadly, not our supercapacitors from Skeleton, but supercapacitors have been used in automotive in 12 volt board nets a lot for start-stop, for example, because you can cycle them a lot. You can discharge them a lot, and you can get always the power out for cranking the engine. And they are also used in some niche applications like 48 volt active suspension, where you have basically an electric suspension for quite fancy cars. But today, the automotive industry is kind of a niche business for supercapacitors. It's growing quite a lot, and there are a lot of new applications coming up, especially on the board net side. So things that run your windshield wipers and everything, those also run your braking and steering in the future. So that is quite important that you have enough power there. But today, where you see supercapacitors mostly is in transportation, in grid installations, and in industrial applications. And there it is mostly about energy recuperation. So you have, for example, supercapacitors on elevators, where every time the elevator goes down, you recuperate some energy. It goes up again, you can use that energy. We have installed supercapacitors together with our customer Skoda Electric, for example, on light rail trams, where they also, when the tram brakes, you get energy back, and when it accelerates, you use that energy. And that's a great application because you save around like 30% energy over the whole use case. And you cannot use a battery really, because imagine how often per day a tram brakes and accelerates. It's a couple of hundred times. So in the end of the day, your battery would be dead. That's where you use supercapacitors. And in grid applications, it's another thing. It's mostly about power stabilization. So as you know, today we run our grids mostly on nuclear power, on coal power and gas power, but that is changing. So in a lot of countries already today, you have 40, 50% of renewables in there. And renewables have this one downside. They're overall great and we should use them more, but they have this one downside that they're not really stable, especially in short term. So you might have some clouds going over the sun. You might have wind going stronger and weaker. And that means that you need to shave out these power fluctuations. And that you can also do with supercapacitors. And we have built up a 50 megawatt installation in France with one of our customers, where you get 50 megawatts for 3 seconds. So it's completely different from the battery case, where you normally calculate in kilowatt hours. With supercapacitors, you often calculate in megawatt seconds.
Interesting. So then, since this is a material science podcast, I want to get into kind of, what materials are ultracapacitors commonly made of? And then we can kind of dive into your technology more specifically.
Sure. Supercapacitors mainly use a carbon material as active material. And other than that, they use quite simple materials. So you can build a supercapacitor, not one that is very close to the industrials, but you can build one in your kitchen because it's activated carbon, which you often have in water filters. It's some kind of electrolyte, which means some salt dissolved in a solvent. And you need 2 electrodes made out of this activated carbon, and you need a separator in between. And I know that you can make one in your kitchen because there are YouTube videos where people make those in their kitchen. Of course, a battery is much more complex. A battery, you have metal oxides and graphite and all these different materials. With supercapacitors, it's fairly simple. So today, supercapacitors mostly use aluminum foil. You coat it with a carbon material. You have a separator that separates the 2 electrodes. That can be something simple, such as paper. And then you fill it with an organic electrolyte. And that's basically it. You don't have lithium, you don't have cobalt, you don't have nickel, or any of these complex materials inside.
And so it sounds like you're creating a symmetric cell, which would be the most analogous to a battery, where you have the same electrode on either side. For actually using a supercapacitor, what stops charge from immediately jumping over to the other electrode while you're trying to charge it? And then when you're trying to discharge it, what physically occurs to allow it to complete the circuit?
Yeah. That's a great question, because it's a question that many people stumble upon. Because if you tell somebody that a supercapacitor is 2 electrodes in a salty liquid, then you would always say, wait a minute, we all have learned in school that salt water conducts electricity. But the difference here is the voltage. Yeah. So if you have an aqueous supercapacitors, you don't go over 1 volt, because then you have exactly the current jumps over, or the voltage jumps over. In organic electrolytes, you can go to 3 volts. That is also quite market standard by now. And what prevents the charge from just going over is exactly the energy storage mechanism itself. So you have charge accumulating on the electrode. You have ions moving over of the opposite charge, forming the so-called electrochemical double layer, which then is the exact charge separation. And the electrochemical stability of the solvent and of the ions in question, and of this electrode-electrolyte interface, that is exactly what determines when the charge will jump over. And that is normally the point where you say, okay, this is my maximum operative voltage. I will not go over that. So as an example, if you take today's supercapacitors and you charge them over 3 volt, then you will have a quick degradation in lifetime. You will have things like gas evolution happening and so on. Overall, you will not have something unsafe happening, like with lithium-ion batteries, thermal runaway or anything. This doesn't exist in supercapacitors, but you still have a degradation.
So you have quite an extensive knowledge base in supercapacitors and kind of the comparison with batteries. I was just wondering what motivated you to get involved in skeleton technologies and what excites you about their technology.
Yeah, it was kind of funny because when I did my PhD on supercapacitors, then I thought while doing it, I already realized, okay, it's quite a small industry. I should probably move more to the batteries at some point and find a job in the battery industry. And I did actually some research on batteries as well. But then it was actually the CEO of Skeleton, Tavi, who visited our university, and we just got talking. And 3 months later, I had a job at Skeleton. And what really convinced me to go into this industry and to start working at Skeleton Technologies is that the focus is on material science as the motor of innovation. So you have kind of all these things that we are doing, like increased energy density in supercapacitors, things that go beyond supercapacitors, like our super battery, which is kind of a high power battery based on all the materials that we have developed before. And all these things stem from material science. They stem from material innovation. And that was highly exciting because if you look at all the other energy storage companies out there, then you often see companies that take the same technology as everybody else and have maybe some trick in manufacturing processes, or they maybe have a very good supply chain in order to make their business case viable. But what I really enjoyed about Skeleton was that you come out with something that nobody else has, and you do something for the very first time. And that's always exciting. That was what excited me in my studies and my PhD thesis. So I'm very glad that I could carry that over to Skeleton.
Yeah. So I think that Praneeth and I, as material scientists, we love to hear that about the innovation, like the cutting edge of the technology. And so we would love to dive into what makes your technology so special and what has driven you to join Skeleton Technologies. So it is my understanding that you are launching a so-called super battery in the near future. Could you explain what a super battery is in this instance and how it's different from just a regular ultracapacitor and what your company hopes to achieve with this technology?
Absolutely. So I will go a little bit back in time to give you also the motivation behind the super battery and how we actually came to it. Because when you think about it, we were basically in 2014, 15, Skeleton was in this position where we had this unique material, curved graphene, and you can increase energy density in supercapacitors with it. And you can not increase it a little bit, but increase it by 80, 90% even. In the end, now in the industrialization phase, we settled on around 70% energy density increase. But in around 2016, when we had nailed that material down and we knew, okay, this is how we will go forward, now we just need to scale it, just as in air quotes, then we realized, okay, there is so much more market out there where you need even more energy density. So we started calculating a bit, okay, what kind of energy density can you get out of a supercapacitor if you had your dream material at hand? So if you were some kind of molecular magician and would be able to hand build a 3D material, a carbon material, then we realized the maximum energy density that you can get out of a supercapacitor is around 30 watt-hours per kilogram. And that was not there where we wanted it to be. So we said, okay, if the theoretical limit of the technology is at 30 watt-hours per kilogram, then we need to kind of switch technologies. We need to get our material experience out there and innovate from the material, how we did it with supercapacitors as well. So that's when the idea for super battery was born. That was on 2016. We then stood a long 4 years in the lab. In 2020, right in the midst of the corona pandemic, we said, okay, now we have the material concept that we want to bring into an industrialization, but we want to bring into the actual product. So we started doing that, and now we are exactly in that phase. 2024, we want to bring the technology to production. So what we did was we looked into different ways how to increase energy storage. And of course, if I'm saying increasing energy storage, I mean, you have to go away from the charge separation. If charge separation has that one limit, 30 watt-hours per kilogram, you need to bring in exactly what batteries do. You need to bring in some kind of chemical reaction. But what we didn't want was a chemical reaction that slows everything down so that you just build a bad battery. We wanted to build something that is right in there that can store energy for a reasonable cost for around 5, 10, 15 minutes. And after that, the traditional lithium-ion batteries can take over. So what we did is we looked into different material concepts for high-power batteries. We looked into completely new materials as well. And in the end, what we came out with is still I would call it a high-power battery, because it has an anode, it has a cathode, but it is at the same time very close to the supercapacitor in terms of life cycle. So you have 50,000 cycles that you can get out of this, much more than out of any lithium-ion battery. In terms of energy, it's 10 times more energy dense than a supercapacitor, which still makes it around 4 times less energy dense than a lithium-ion battery. And right in that middle, there are a lot of applications. There are applications where it's mostly about you want to charge very quickly and then use maybe for 15, 20 minutes. You want to have very high power. At the same time, you don't need a lot of energy. Couple of examples, if you have any application in intralogistics or in mining, where you have a fixed route. So for example, a mining truck goes in the mine always the same route, maybe 5-10 kilometers. And it always stops at the same stopping point. So it needs to basically take a bunch of ore, transport it somewhere else. Then you don't want that mining truck to stand in a corner and charge for 2 hours. You want it to run 24/7. So ideally, you can charge it in that 1 minute or 2 minutes that it is standing somewhere and getting loaded up. And that's exactly one of these applications where exactly the energy to power ratio is perfect for super battery.
I want to challenge you on one thing here. So there's another company in the US called Natron Energy, which is doing a very similar application, but they're achieving this with a sodium-based battery. And so for that, they're using a different chemistry with a higher voltage to achieve the same type of higher energy density, but it has worse cyclability, and like it can quickly discharge 15%, but like you said, it doesn't last very long compared to lithium ion. So my question to you is, they're using a different chemistry, but you're trying to approach it with ultracapacitors. Could you go into a little bit more about how these capacitors are allowing you to get to the super battery just from not like changing to a sodium-based battery like a lithium-ion battery would be?
Basically, if you compare our supercapacitor technology that is in the field with the super battery technology, then from material perspective, we still use a lot of the same materials. We still have aluminum foil, we still have a separator, we still have the same electrolyte, we can use the same cell form factor. And the one thing, we even still have a lot of carbon in the electrodes. The one thing that we do is we add a specific, let's say, anode and cathode material that we have mostly developed ourselves, how this combination works, in order to get added energy storage. And for us, it was very important because we analyzed the market. It was very important to have this extremely long life cycles. So we needed to have very high cyclic stability, but it was also important that we do not go in the direction of having materials in there that are very scarce, so cobalt or anything. And in terms of comparison with sodium batteries, then of course, there are a lot of applications where sodium batteries also can be used. Mostly those sodium batteries are rather looked at as this, let's say, cheap battery that you can store a lot of kilowatt hours for €1 or $1, but you don't get a lot of power out of them. And I understand every battery works like this, that you can always get a little bit of peak power out of it. But for us, it was important that you can get the full charge in 1 minute. And that is something that I think also sodium-ion batteries or lithium-ion batteries can rarely do.
So you mentioned this application in mining, for example, and I just wanted to understand what materials were used originally and like how much more efficient this super battery technology can kind of make that space in that specific application. Can you provide any sort of comparison there with what's used previously versus what can be used? Because obviously there needs to be like a business case to invest this amount of money and time into developing this new technology.
So the business case here is a little bit more complicated because I can tell you what is used today. It's a very common material called diesel, which is used. So if you, of course, have a fossil fuel combustion engine, then it's very hard to compete with that kind of cost per power, cost per energy. But the driver here is not that you get cheaper. The driver here is that you get the cheapest solution that still adheres to regulation, and the cheapest solution that still gives you something that the customer will want to buy. What is happening at the moment is that more and more industries are looking into carbon footprint along their whole supply chain. So if you can actually supply raw material out of a mine where you can put a sticker on it and say, I have mined this with that much less CO2 because I use electric mining trucks, there's a value in it. If you compare this with the other approaches of electrification and mining, for example, classic lithium-ion battery, why don't you just use a bunch of Tesla batteries or anything and put those onto a mining truck? Then you certainly have enough energy density, but you can calculate that if you charge this battery around 3-4 times a day, you lose around, because you want to work 24/7, you lose around every time 1.5 hours for charging. So that's time that the truck is not driving. So for that time, you need another truck. So you need to buy more trucks. That's point number one. Point number two is if you charge 3-4 times a day, then you have every year around 1,000, 1,500 cycles. That's the lifetime of a lithium-ion battery. And that means that every year you need to buy a new battery. And if you use our super battery, then you have these two effects. You have very high utilization. You can use the thing basically 24/7 because the time when it is charged is time when it is also used, loading and unloading. And the other effect is you don't need to replace it every year, but you can use it for 5, 6, 7 years. And then when you anyway need to do the whole maintenance in a mining truck, you can do that as well.
And so what in your super battery is the breaking point? What allows the degradation of the capacity to the point where you would need to replace it?
The super battery can cycle around 50,000 cycles before you need to replace it. And that's around, depending on which battery technology you choose to compare, but compared to very good lithium-ion batteries, that's around 20 times more. So compared to the average lithium-ion battery that you have on your phone, it's around 40 times more. You can just check your phone. Normally, your battery starts to be a little bit iffy after maybe 3 years. That's 3 times 365 cycles because you charge it every evening. So it's around 1,000 cycles.
That's awesome. Wow. So, and you briefly mentioned the year 2024 in a previous answer, and that seems to be a very important year for Skeleton Technologies because you plan on opening the largest supercapacitor factory in the world in 2024, which is estimated to be 40 times the capacity of your current factory. So we were just wondering what is driving that decision to scale up to that extent. Is that demand based? And what did that decision look like?
Yeah, so of course we wouldn't build the factory if there was no demand. I can tell you that.
Right.
So our current factory that we built up in 2016, 2017, that factory is, with all the extensions that it has gotten over the time, at complete capacity, basically. So we knew that this time would come, that we need to build a new factory. So the supercapacitor market is part of the energy storage market. And while it is a niche in the energy storage market, the energy storage market is so big that that niche becomes quite big as well. And if you look at how the energy storage market itself is growing, how many terawatt hours we need in batteries every year and in energy storage every year, then you can imagine how many supercapacitors we roughly need. The factory output that we have planned for this new factory, that is actually covered by orders and also by agreements with customers, so frame contracts and so on. So we know that we will need this capacity. The interesting part will actually happen after this first phase of the factory, where the factory actually offers enough space to build more capacity into it. And we also have plans already to build out more capacity. So this is just the first step. And I would say that if you are today in energy storage and you have a product that halfway fulfills the requirements that your customer wants, then you are almost certainly scaling up.
And so when you build such a large demand, what are the scaling issues that you need to go over? Like you said that before, you just need to scale. But what problems do you foresee having with such a large increase in capacity?
Yeah, so there are two things to consider here, because Skeleton is not only a supercapacitor manufacturer, but it's also a materials manufacturer. Of course, we are the only customer of that material, but it is very different to scale material compared to scaling an energy storage technology where you have to scale cell manufacturing and module manufacturing. So let's start with the easy part: cell manufacturing, module manufacturing. It's not something, of course, that you can do with 3 people or so, but it's something that you have today a lot of players in the field that have scaled battery factories and that have the experience so there's a lot of experience in the market with the machine suppliers and everything to actually build out a scaled plant. For material, it is very different, because material scaling always is an individual case. It depends very much on how you synthesize your material. It depends very much on what is the exact supply chain behind your material. Even where can you build such a plant from regulations perspective, which is with chemical industry always a bit more complicated. So that is the harder part that we have been working on, and we are now in a very good spot where we are already working on the scale up in terms of hundreds of tons. And the hard part is over, where you work on the scale up from a couple of grams to 1 ton. Yeah, that is the hard part. This is something that also took longer than expected. So I think to everybody interested in material science out there and interested in how to scale a material from lab to industry, it always takes longer than you think when you stand in the lab. But you need to basically just be aware of it and make sure that you, from very early on, include the right people and include people that have done it before, because that is the one thing that we realized quite quickly. Okay, we need to get experience in there with people who have scaled before.
I'm curious, how early in the process, or how early is that process development team incorporated into that the scale up state, or the scale up process? Because in the medical device industry, I know we've learned that it's important to bring in the manufacturing team, the process development team, as early as kind of that lab stage where R&D is heavily working on that. I'm curious if that also translates to this supercapacitor space and skeleton technologies as well.
Absolutely. We basically have anybody who is working in the lab on something that we intend to put into production. So basically everything that the people are working on in the lab is already aware of the kind of ground rules that you need to follow in order to make that scalable later. So nobody's working on materials where we know they are too costly. Nobody's working on materials where we know, okay, they're not sustainable or they're too toxic. It's very different from, let's say, academia, where you often do material research in order to find out which properties give you the kind of best value, and then you care later about how to do away with the disadvantages. So what we rather do is we start already in the lab in the very first phase. There's a checklist where you need to go through. Is that even something that I want to consider? And only then you start even with the very early lab tests.
What do those ground rules look like from the processing standpoint? Like you mentioned, sustainability, cost definitely makes sense. What does that look like in terms of estimating in the future? Can this be processed at a larger scale and industrial scale?
I think this is the easier part often, because when you work in a lab, then you normally don't want to use complicated processes yourself.
Yeah.
And you want to use aqueous coating, or you want to use water in your processes. You anyway want to kind of not work with the most toxic substances, and not have, also you don't want to ask for the budget for some couple of millions for some plasma vacuum machines or anything. So I think that is something that goes alone with it. But of course, that's also part of the checklist, that you kind of the if you categorize what kind of materials and processes we want after, then on the highest score, you will basically get if it's the exact same processes that we use today. If we don't have to change a thing, because Skeleton already is using very sustainable processes. We use water in our coating. We don't have any organic solvents that we need to get rid of in the factory or anything. So that's basically the way how we do it. We categorize it. Okay, how far is it from what we do today?
Now that you've walked us through how you're going to scale it, let's go fast forward to 10 years in the future. And so this will be a two-part question. So the first part is, where do you see supercapacitors starting to enter the market into more, and their relationship with batteries? Will they overtake batteries in some cases, or will we start to see more of a cooperation between the two? And then the second part will be, how do you think your super battery will start to enter into the market, and how will that evolve over the next 10 to 20 years?
The supercapacitor market definitely is evolving jointly with the energy storage market. And what is the driving force over the next couple of years definitely is renewables, grid, and transportation. So in transportation, especially in rail and truck transportation, we see really a drive to save as much energy as possible. And there, this kinetic energy recuperation plays a big role. And for kinetic energy recuperation, you most of the time talk about events that last a couple of seconds. So you want to have something very powerful there. Supercapacitors are well made for this. In the grid energy storage, as I said before, today our grids run on coal plants, on nuclear plants, and those things have these huge rotating turbines which stabilize the grid just by being huge and rotating. And the more you take those out and replace them with smaller solar and wind and so on, which is a very good thing, the more you destabilize the grid. So you need to stabilize it again by bringing in very reactive energy storage. And lithium-ion batteries are not very reactive. Lithium-ion batteries are great for storing, let's say, energy over a couple of hours and then releasing it at night, but they're not very good at giving you 50 megawatts for 3 seconds or 150 megawatts for 3 seconds. That's where supercapacitors will come in, and that's where we also foresee quite a large portion of the market. And then, of course, you have a lot of electrification happening generally in industrial applications, in intralogistics, in construction machinery, where the boundaries between supercapacitors and batteries are kind of flowing. Yeah? So sometimes people rather choose a battery than a supercapacitor. Sometimes they choose a supercapacitor because it really depends on the individual application. And that's also where you have a little bit the starting point to the answer. What do supercapacitors do in terms of in their relation to batteries? I can give you the clear answer. They will not replace batteries. Batteries are, especially lithium-ion batteries, they're great at what they do. They store energy, and they also evolve. They also get more powerful. It's definitely the larger part of energy storage that will be done with classic lithium-ion batteries, where you have NMC, LFP batteries. But supercapacitors will definitely be used together with batteries, and especially with batteries that have very high energy density, very low power density. So LFP batteries, for example, are one thing, and batteries that are very cheap. So that you can basically have a battery that isn't very powerful, especially at minus 20 degrees C. But for that, you add a small supercapacitor portion so that you can still have the main critical functions of that battery pack is supplied. And that is where we really see the future supercapacitors working together with lithium-ion batteries. Now, for the second part of the question, for the super battery, this is, of course, technology that competes more with the battery itself, but it competes also in a field where lithium-ion batteries would also not be chosen otherwise, but rather the customer would choose not to follow up with the project. So the customer would rather just say, okay, I will just wait until there's a better technology, and then I will use that. Reason for that is that the projects otherwise will be too expensive, or you will just have a too bulky energy storage. So super battery, if you look at which markets it will start with and which markets it will basically evolve into, then definitely the starting point is heavy duty and intralogistics, because there you have exactly these use cases where you have extremely high utilization. So you don't want the machine, whatever you're talking about, standing in a corner charging, and that's what super battery is very good at. And you have still a need for quite high energy density compared to supercapacitors. So supercapacitors are not really the choice there either. This will evolve into transportation and automotive a lot, because in transportation, you have a lot of talk about hydrogen as an energy carrier for fuel cell vehicles. And fuel cells are very great when it comes to energy, but they're very bad when it comes to power. And they always need this power battery to support. So that's where also the super battery can play a huge role. And finally, in automotive, you have either fully electric vehicles that then just have much less range, but you don't need a lot of range because you anyway just use them in the city or you use them in like smaller routes. Or you have fuel cell vehicles, or you even have hybrids. Yeah, so hybrids still will play a role in the next years to come, where also the super battery will then support those use cases.
And so now maybe a hard question for you, but you focused a lot on stabilizing the beginning of grid. But I think that as in the next 10 years, as electrification happens, we need to stabilize the other side of the grid where the user will use it. And so that comes up in microgrids or having packs of batteries in each of the households. How do you foresee that playing in the role of the super capacitors in that application?
I think supercapacitors will not play a huge role in this specific one where you have the microgrids. We actually have built up some microgrids with supercapacitors as well. Industrial microgrids, for example, where you have in industrial applications power peaks. So you have industrial machines that just require so much more power, but require that power only for a couple of seconds. And of course, somebody in owning an industrial plant, a manufacturing plant, is very interested in power stability and in having the machines always run smoothly. For let's say you and me having an apartment or a house where you want to stabilize your power, it's not that critical to have actually high power density. The worst thing that happens is that you cannot use your most high power devices in your household for some time, and that your own microgrid will tell you that you can now not use the washing machine or something. So here I think the supercapacitors will probably not be used too much, but it's also not let's say the industry is a much more high power user of electric power than the average household. Yeah.
So just focusing more on the big users and we'll figure the rest out by ourselves. Okay, very interesting.
Can you tell that David's very interested in batteries? He's asking the tough questions.
It's a very good question because it's always, I think you often have in energy storage these fairy tales of people telling you that their energy storage device will be found everywhere in the future. And it's mostly not true because you have different applications and not one size fits all. So I think in this case, for the end user in the house, a classic lithium-ion battery is perfect. It will get very, very cheap in the future, and you don't have power peaks in your house. So unless you're doing something crazy. So I guess that's not the average use.
Yeah.
And throughout my time in the energy storage field, I've heard, I guess I could say, negative opinions on capacitors and how batteries will always remain superior. I guess you're on the other side of the opinion and you're very pro capacitor. And I think that through the conversation, you've shown a lot of improvements. I guess if there are any more doubters out there, what steps are you guys taking to address any issues that might still be lingering about any hesitation?
I think the main step is actually pointing out which application you are talking about, because the main criticism towards supercapacitors is energy density. And I fully accept that criticism. It is a fact, supercapacitors don't have the energy density that lithium-ion batteries have, because they are not required to have it. You use them in different applications. And it is also a fact that lithium-ion batteries or other batteries don't have the power density that is required for some other applications. So that's point number one. Of course, on the other side, you can say that Skeleton has been always working on the weakness of supercapacitors, which were mostly two things: energy density and scale. And scale, we already talked about the new factory that we are building. So that scale will bring the costs down. And energy density, on the other hand, we're working on our curved graphene material that has more energy density in supercapacitors, and of course our super battery technology, which is also based on new material innovations. So these are exactly the gaps that need to be worked on. We're not the only ones working on them, but this is the way to go forward if you have any technology. And the same way, lithium-ion batteries are working on having higher power, working on having lower cost, and working on having better sustainability.
Absolutely. So then kind of to wrap up this episode, we have a lot of listeners like David who are interested in energy storage, right? Specifically from the material science and engineering perspective. So we would just love to hear your final piece of advice for younger MSEs who may want to join the energy storage space or make an impact specifically in supercapacitors or just the industry as a whole.
I think my main advice is early on in your career as a scientist, start investigating what the industry actually is doing, what kind of materials are used there, what processes are used, and try to find out, maybe by just calling somebody, just writing people in the industry. Actually, a lot of people like me are happy if students write them and we will answer. But try to find out what would be an actual innovation. Because what you see in a lot of publications, and that is not only publications of like young scientists, but even very veteran scientists, that these publications are written basically on one path that is completely parallel to the industrial path, and those never intersect. So in the sense that you have some materials that would actually not be used, or you have some processes that would actually not be used. So what I wish that somebody had told me as a young scientist is look into the real application and try to understand how your material work actually impacts the application. And one final advice is think always about cost, because that's the thing that at least in a lot of labs is not discussed a lot. And it's great to discuss cost. You can actually find out so much about an application when you break it down into cost items.
I love that. Yeah. Thank you so much, Sebastian, for joining us today. That was a really fascinating conversation. I learned a lot about supercapacitors, and then I know David challenged you on some stuff, but also really asked some great questions as well. So we really appreciate you joining us today. It was a pleasure having you.
Thank you for making this possible to be on this podcast as well. I've enjoyed it as well. And challenging questions are always welcome, of course. Without challenges, we don't grow. So keep them coming.
Awesome.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.